Okay, so on the agenda today, there's my quick intro. I have three slides, including this one, and then I'll hand over to Jeremy, James, and I'm sorry, there's actually going to be a third person presenting, isn't there?
Lauren could present as well.
Yeah, sorry, Lauren, missed you out of the slide. And yeah, we'll be talking about a project, trying out AI systems on FPGAs using oneAPI and talking a little bit about the oneAPI construction kit. So, uh, this call is a call for the UXL Foundation Hardware Special Interest Group. So, on the right on the slides, there's kind of overall structure of UXL, with a steering committee at the top. Then, of course, under them, there's special interest groups and working groups. So, we're a special interest group. That means we don't cover anything confidential. This meeting is essentially public, and we aren't directly responsible for delivering anything that UXL does, because that is the purview of working groups. We're just a group of people who are interested in a topic of relevance to UXL. And for the hardware SIG, that's hardware abstraction and how to support software on hardware. Historically, the hardware SIG has covered things like level zero, the unified runtime, the LLVM offload interface, and the oneAPI construction kit. But that's just what we covered in the past. It could be that we cover anything which comes under a whole general topic in the future. And it's been a few months since we last had this call. So one thing that's happened since then is the oneAPI construction kit has transferred ownership to the UXL Foundation. So the code was open sourced under Apache 2.0 back in February 2023, but in November last year, the ownership was transferred to UXL. The aim of that is to make it easier for external parties to participate and for them to have a more true sense of ownership via the UXL Foundation. The code engineers who were working on it before continue to work on it, and we're also have been setting up improved CI for it within the UXL Foundation. But that really is all I'm going to say. So from here, I can pass over to Jeremy.
Okay, right. So, thank you very much for your time. Context. NVIDIA, depending on who you read, has somewhere between 70% and 95% of the world AI market with its GPUs and its CUDA software. Now, this is a technical triumph and business triumph for NVIDIA, but it's very bad for the future development of AI, because diversity is essential if we're going to take this technology forward. So the question we're going to leave you with today is, how do you get AI running competitively and efficiently on new hardware? That's, of course, why we're all here. I'm Jeremy Bennett. I'm Chief Executive of Embecosm. I'm joined by William Jones, who's my head of AI, and who incidentally is responsible for the national guidelines for best practice in AI for the electronics industry through TechWorks. And I'm also joined by James Betson and Laurent Beer from the University of Southampton, and they're going to be presenting the hard practical case study from this talk, and I'll talk more about that in a bit. What I want to start with is by talking about the context in which we do this. And I appreciate that for many of you, this will be obvious and trivial, but it makes sure we're all on the same page. I'm going to focus on neural networks, and I'm aware that there's much more to AI than just neural networks, but it's the big player at the moment. And whatever your choice of representation, whether it's TensorFlow or PyTorch or JAX or Onyx or whatever, all these systems end up representing a neural network as a graph, a set of nodes And you walk across those nodes, and those nodes have some inputs, some weights, and some outputs, which are represented as vectors of varying dimensions, the tensors that we here refer to. And to carry out training or inference, you walk over that network, evaluating each node as you come to it. And in terms of the gross structure of the software, all these tools look roughly the same. You have a graph evaluator. It looks at each node. It looks at the tensors it needs and it's going to generate, and indeed tries to be reasonably clever about where it puts those tensors because they're big and you don't want to copy them around. And then it works out how to evaluate the operation. And all these systems are based on a host and accelerator view of the world. That host and accelerator, by the widest, most common is the host is some form of x86 and the accelerator is some sort of GPU. And the dispatcher must decide which bit of the operation and how it's passed on to the host and onto the accelerator. There are sometimes variations of this, in particular some of the compilation tools, so things like from long ago, Apache TVM, more recently IRI and OpenXLA, give you a level of graph transformation, say, can we make this graph slightly more efficient to evaluate? But fundamentally, the same approach. And our focus today is on this bit, the dispatcher. Before you worry about optimizing your graph or anything, you've got to get the system working. So the question is, if I want to run on a new sort of accelerator, RISC-V, say, I'm going to have to work on the dispatcher. And how do we work on that? How do we bring up that dispatcher on new hardware? I'm not going to worry about how you bring up the graph level transformation, though the graph level transformation does not operate in a vacuum. It does know about its back end. It will do things like partition operations to take advantage of, say, gem units on the hardware. And how you do that partitioning is very back end dependent on the size of your gem units, for example. So the dispatcher. And this story is the same whether you're doing really big chips, and this is one we've worked on. It's got more than 1,000 RISC-V cores. It's got a load of gem units on it for doing the matrix operations. And of course, it's got a host, which has got plenty of cores on well. So that's a huge, great system. But it also is just as applicable to the smallest systems. And on your AI-enabled microcontrollers, typically you're only going to do one operation at a time, whereas big systems, you might want to do multiple nodes of the graph, multiple operations at a time. On a small one, you're doing one operation at a time, possibly with some specialist accelerators who can perhaps speed up map-mul or convolution or something like that. And you've probably got a smaller number of cores, 2, 4, maybe 8. And there are systems within these systems, ExecuTorch if you're inside the PyTorch world, or LiteRT if you're inside the TensorFlow world, what used to be called TensorFlow Lite for micro. So this model applies to all of them. And a lot of what we do is people tend to talk to us because mostly we work on compilers pre-silicon. So you can do all this pre-silicon, that big, super high performance system I showed you. The first thing we did was to bring up a QEMU model just to check that their idea of how things would hand off would work as they expected. This is not going to give you anything useful in a performance thing, but it'll show you it is functionally consistent. And we used the private use one interface of PyTorch to offload to the QEMU model of the accelerator using memory mapping. So again, the same model applies. And let's now look in how oneAPI comes in here. Okay, I'll put it in the context of PyTorch, though in principle the same applies to other approaches. Okay, so there's my dispatcher at the top, the tensor assignment, the operation evaluation. Then you've got target selection. So you've got that target needs to have an implementation of each node corresponds to an operation. So your neural network node, it's your operation. Those operations will have an implementation. Now, there are plain reference implementations in C and C++. They're not terribly useful to you because they have no concept. They're completely abstract and generic. In our circumstance, the operations are implemented in SYCL, possibly OpenCL, but SYCL. And as of PyTorch 2.4, there are SYCL implementations of about 600 to 800 of the commonest operations in PyTorch. And that operation will have been compiled into a multi-arch ELF. So you've got code that's going to run on your host and code that's going to run on your target. In this case, we were doing it for RV64, so RV64. And that code on the target will run on the target, and on the host code, you'll have OpenCL API calls to control what's going on. So that's the high-level picture of what we're generically trying to do. And in terms of implementation, how do you bring this? Because OpenCL, it's 20, 25 years old. It's a big, powerful system. And it takes a while to implement OpenCL, and you want to bring up things fast. Well, there is an implementation of OpenCL, which of course is the how, the oneAPI how. That is a hardware abstraction layer that understands about parallel accelerators. And rather than implementing the whole of OpenCL, I can provide an implementation of the oneAPI how on my system. And that's something we reckon we can do in about 3 months. You come along with your new chip, and we can get the oneAPI how going in around 3 months. And that gets you going. Your operations will be picked up, they'll be dispatched, they'll be run. Okay? And that's a really good starting point for getting going. And if you're running on a small machine, if you're one of those microcontrollers, probably all you need. But if you want to go really fast, the how is simple because it's more limited in its functionality. Ultimately, you'll have to implement the full OpenCL library. And of course, OpenCL gives you the functionality to run in a truly parallel environment where you don't have to say, here's some arguments, I'll wait for the result, but you can hand off a handle to the result and only call upon that result when you actually need it at some time in the future. You're probably going to have a very lightweight OpenCL runtime API actually for your actual accelerator. These are powerful machines, and just treating them as bare metal is not going to get the best out of them. So that's, if you like, a high-level view of what we as people who implement these things go through when you come to us with new hardware. And that's all supported by the oneAPI construction kit. And when we look at this diagram, everything white is pretty much standard. The only things you have to provide for your new hardware is obviously the hardware, that's the big green box at the bottom, a compiler for your hardware, because you've got to be able to compile this stuff. In this case, there's an RV64 compiler for SYCL and OpenCL. And of course, the back end, and that's where the hardware abstraction layer makes it easier. So you're going to have to provide your back end for that there. So a lot of the stuff is already done for you, and the host runtime is all there. When you get to the full implementation, you're looking at the RV64 runtime and a more sophisticated back end. But the oneAPI construction kit gives you that story. So that's a general context we're operating in here. Now, I want to talk a bit about the challenge of where we are in the real world, and this impinges exactly on what we do as a company, increasing part of our business. Well, let's look at the world of AI. There are millions of people who use AI in the world in the sense they play with ChatGPT. There are even AI systems that play with AI systems to run ChatGPT. So you can see in my little diagram, I've got these little silver robots representing that. The interesting layer, and this is where the big changes are coming, is people using standard models in applications. Okay, now a lot of that is ChatGPT or equivalent large language models, but it's also people doing image processing using things like ResNet type models and so on. But they're using standard models, and they're not creating models. They're taking the power of models for various applications people have created. And again, lots of people doing that. And that's actually where the true changes are happening in the use of AI across wider society. What there's relatively few of is people writing AI models. Okay, the people actually writing new AI model, as opposed to, and I really mean new AI models. I don't mean someone slightly tweaked a standard one. They put another layer into ResNet, so they've got ResNet 19 instead of ResNet 18. Doesn't really count. But writing completely new models, that's a relatively small community. Some of that's very radical. Some of it can be groundbreaking. Think of AlphaFold, and that won a Nobel Prize for its work. So there's a small community who are doing the really novel AI models. But sitting at the top of all of them are these guys, the people who do AI tools. And some of that is automated as well. Okay. And that's where we fit in, and that's what this talk is about. Okay. Now, how do you do this up? Because that community is small and there aren't enough AI tooling engineers to go around, and quite a lot of people we talk to are people who've run into problems trying to do it themselves. There's really good tutorials. For a small machine, PyTorch, LiteRT, they're online. When we were doing the QEMU modeling pre-silicon, we were using private use 1. That's documented. SYCL OpenCL, it's in PyTorch 2.4, and there's a link. These slides will be shared afterwards. There's a link to the starting page there. And the oneAPI construction kit, that's freely available on Codebase GitHub. A lot of the way we do, we're an entirely open source company. A lot of the way we advertise our services is telling people how to do our job. So I'm working on the first of a series of how-tos on how you bring up AI tooling, and those will appear over the coming months. I'll come back to that in a moment. And lastly, of course, we are a commercial company. If you want our help, please come and ask us. We'll be very happy to see if we can assist you. So that's, if you like, that's me as chief executive giving you a big hand-wavy picture of how it all fits together. But this stuff is only useful if it's in the real world. Those how-tos are growing out of some work we did last summer. Will Jones, my head of AI, and I supervised the 4th year group design projects at Southampton University. James and Laurent are 2 of a group of 6 we supervised last autumn. And they're going to present a case study where they brought up a new AI system on new hardware using the oneAPI construction kit. They'll talk about what worked and didn't work, and that is going to become the basis of the first how-to that we publish later in the year. So at this point, I'm going to stop sharing. I'm going to hand over to James and Laurent, who are going to talk about this use case, and that will be the big part of our talk. And we're very much looking for this community to inform what we do. This is all relatively new to us as to everyone here. It's a fast-changing world. We'd like to hear from you what we've got right, what we've got wrong, what would really help you in the future. So thank you at that point. I'll stop sharing and hand over to James and Laurent for their bit.
Great, thank you, Jeremy. Just going to share my screen now. Great, can people see my slide?
Yes.
Okay, brilliant. So, yep, thanks for the introduction. And as Jeremy said, it'd be great to hear any kind of questions and feedback, and we'll have hopefully some time at the end to engage with some things you have to say about what we did. Anything that can be improved in the future would be interesting to hear. So welcome to myself and Lawrence's master's presentation, where we'll discuss a little bit about our master's project, Hardware Acceleration for PyTorch, a demonstrator undertaken with Embecosm. So just change my slides. First things first, let's meet the team. So we're a group of 6 master's students from the University of Southampton, mostly comprised of electronic engineers, as we were sort of quite drawn to the FPGA aspect of the project. And it's safe to say that between us, we had sort of little AI tooling experience before going into the project, as our expertise sort of mostly lied with low-level software and hardware. But we thought this provided quite an interesting perspective to the problem that Jeremy's sort of set the scene for. Can a group of underexperienced students use the existing AI tools available and the existing AI documentation available with their own hardware accelerator? Can they bring something up? Can they build a project, something useful? And this involved investigating if this was easy to do and what sort of process a group of engineers such as ourselves would have to go through to bring up this physical project. We'll talk about the project later, but first let's set the scene and extend what Jeremy has introduced. So PyTorch, what is PyTorch? Well, it's a C++ framework that presents a nice, easy to use Python API for users to make neural networks. And it's a little bit like this iceberg that I have here on my slide. The user sits at the top and uses simple Python programs to access a large C++ code base underneath, which does all of the heavy lifting associated with training and producing neural networks. It's used by many large companies like Meta, Apple, TikTok, just to name a few, due to the sort of quick, seamless development lifecycle it offers engineers, which is, of course, a huge bonus. So how does PyTorch work? Well, the framework converts the training of neural networks into a series of mathematical operations, which, when run in a particular order with a particular set of operands, facilitates the back propagation and producing of the neural networks. The operations, along with their operands, are run inside software environments called kernels, as you can see in the green bubbles here in the image. And these are all run on particular hardware endpoints like CPUs and GPUs or custom hardware, for example. Okay, this sounds great, but is it completely perfect? Well, as it stands in the current state of the art, PyTorch has great support for CPUs and GPUs. And this is particularly great if you have a NVIDIA GPU lying around, because you can make use of its massively parallel SIMD architecture to really speed up your neural network training. But what about custom hardware? What if you and your engineering team had their own custom ASIC capable of accelerating matrix convolution? Or perhaps more likely, what if your team had an FPGA design that they wish to use with AI tools in their kind of current situation? How easy is it for that team to integrate their custom hardware into the AI tools that already exist?
So as James have already said, PyTorch does support major existing hardware platforms such as GPUs, CPUs. But how does it actually do that? So whenever a PyTorch operation is run, it invokes the dispatcher to offload the compute onto the kernels. And the kernels are the things which actually run the PyTorch operations: matrix addition, convolution, batch normalization, just to name a few. And so for each of these operations and for each of these hardware platforms, there exists a kernel. However, it becomes a kind of an issue when we are trying to add our own custom hardware accelerator, because that means that for every operator, for every operation, we would have to rewrite a specific kernel for our own hardware accelerator. And this means that we have to rewrite thousands and thousands of operations, which is a lot of work. So if it's so much work, why should we do it? Custom accelerators can be quite useful. I mean, we can get improved performance as we can leverage their specialized design and their hardware, where custom accelerators are sometimes designed to perform specific tasks such as matrix multiplication much faster and efficiently than general purpose CPUs. We can also get some other traits such as increased energy efficiency, reduced latency, and scalability. And also they can provide better flexibility by utilizing heterogeneous compute architecture, where we basically get more performance out of the same space. And it also provides us with the additional flexibility as mentioned. However, the problem is that with utilizing custom accelerators is integrating them with the programs. Users must still develop and interact with the software stack at some point. So there is a need for some sort of system or solution that allows an easier integration of custom accelerators. And that brings us to our project. So the problem is that it is difficult currently to add support for new accelerators in eager mode. As to reiterate, we'd have to rewrite thousands and thousands of core operations, which is just an extremely large amount of work. And our job was to investigate how this can be done, do research into it, and then eventually build a proof of concept demonstrator. So how does that work? Well, we start with SYCL. SYCL is a high-level library based on C++. It is designed to enable hardware-independent computation or being hardware agnostic. This means that the code is not tied to any specific hardware platform that it runs on. Underneath it, SYCL runs on top of OpenCL, which is a framework designed to support heterogeneous compute on multiple hardware endpoints. And this is what we use to have this connection, the interface with the hardware. If you look at the diagram, at the top, we start with the user C++ code. And on the right side, that is the conventional compilation process, which is just focusing on generating binaries for a specific platform, but it doesn't support explicitly supporting heterogeneous hardware. On the left side is the SYCL version. So the SYCL compilation employs both the SYCL library and the data parallel C++ compiler, which are specifically designed for heterogeneous computing environments. The SYCL library itself provides a higher level abstraction, allowing developers to write operations which are executable across a range of accelerator platforms. And then all of this feeds into the OpenCL runtime, which acts as this bridge between the compiled SYCL code and the hardware, initializing it and managing offload. This is also what allows for parallelization, and it allows the code to be executed on different accelerators, such as CPUs or FPGAs or GPUs. So let's talk a little about how does it actually do through the dispatch comparison. So on the left, we get the traditional PyTorch offload. So the dispatcher, the operation calls, the PyTorch operation calls the dispatcher, which then calls the backend that matches the operation and the execution hardware. But again, each accelerator requires a whole set of unique backend kernels. So all of these green kernels are for the same operation, but because we don't necessarily know the used hardware, we have to write a kernel for every single one of the possible hardwares that we might use. And this is really a lot of work in itself. So how can SQL make our life easier? Well, on the right, all of those kernels can be just simplified into a single SQL backend, which can then be used for any sort of hardware platform. Here, the idea is that they're running the SQL kernel with no specified hardware, but we rather make a promise that any hardware that we are going to use will be able to execute whatever we run. And as previously mentioned, these are currently mostly optimized for Intel GPUs and accelerators. Yeah. So how did we actually use that? How do we actually achieve this? We use C++ extensions. The current tool, the PyTorch tool, PyTorch uses PyBind, only supports a standard G++ compilation process, which is not feasible for SQL as it uses a VB C++. So we couldn't use that to add custom kernels. However, what we ended up doing is writing our own standard C++ kernels. And then we ended up calling our SQL functions as external functions inside. And then we compile the SQL functions separately into a shared object, and then link this shared object through the export command here shown below into our runtime environment. And then this brings us to our implementation. So the PyTorch calls the dispatcher, which then calls the SQL kernel, and this sends out the OpenCL API calls, which go into the OpenCL runtime. And here we have created our own OpenCL interposer, which sits inside this runtime. And the interposer intercepts the API calls. The point of the interposer is that it extends the operands and it determines the operation code, which are then sent directly to the accelerator. In our design, we did this via TCP connection. And then the result just gets sent back all the way through. And then, so I mentioned the interposer, but let's talk about the why. So initially, we had two ideas of how we might do it. One idea was the oneAPI HAL. We had initial struggles to make it to work as we were inexperienced with it, and we thought that it would require additional work and much more research for us to actually get it to work. And we were also worried about the time constraints of the entire project, as our entire project was only around 10 weeks long. So we were just worried that it's not going to be enough time for us to actually implement it. Another option was to create a custom OpenCL device. But again, here we realized through further research is that it would take way too long, as we would have to rewrite quite significant amount of PyTorch backend for this. And we're also worried about a lot of overhead. So eventually our solution landed on to manually intercept the OpenCL calls onto the SQL default selector device, and therefore the interposer extracting the operands and the operation types. So this was the how. This was the why. Let's talk about the how. So the interposer is connecting. Its SQL kernel feeds into the interposer, which then connects into the hardware endpoint. In that connection to the SQL kernel to the interposer, we have identified two major API calls: the set kernel arg and the onQ and the range kernel. The set kernel arg is the one that captures the SQL data buffer to extract arguments for the kernel. So this is the one that opens up the SQL buffer, and it's also the one that determines the operation type. And once this was done, we let all the rest of the API calls run until onQ and the range kernel. And when onQ and the range kernel is run, that's when we know that we are ready for the operation to be triggered. So we feed all this data into our overwritten onQ and the range kernel function, which then triggers the computation and establishes the TCP link which we then send our data through the TCP link, wait for the response, and then send it all back over PyTorch to PyTorch. So why is this better? Well, we don't need to rewrite more PyTorch source code. We have significantly reduced the backend development effort for custom hardware accelerators, as users now do not need to rewrite their kernel specific to their hardware. And so we could save thousands of hours of work potentially with this, because as right now we just need to use PyTorch as is. And again, before we would have to repeat this process and recompile after any sort of hardware change, which is just extremely tedious. Whereas now we could just interface with the OpenCI API calls, as it is much easier and nicer to just intercept the data for the hardware to run. So again, why is this better? We have managed to shift the user effort away from PyTorch. This also allows to reduce the workload on integrating of the hardware into PyTorch. So this also allows developers to focus on other aspects of the project, maybe to improve their accelerators. And overall, we want to ensure that the AI tools keep getting better and better. We want to ensure this through innovation and diversity in the market to get the best possible results for AI accelerators. And James will talk about our demonstrator now.
Brilliant, thanks, Lawrence. Okay, so that sort of addresses the software side of what we produce in our project, but what did we physically actually create and then bring up? So over the next few slides, I'll sort of go over our system architecture so that we kind of paint a sort of a full picture of what we did. But our solution broadly can be split into two halves. We have a Linux x86 host, which runs PyTorch. And for this, we used a WSL2 environment. And then we have a Xilinx Sync 7000 series SoC, which you can see here on the right. And this is what we use to house our hardware accelerator. So starting with the FPGA on the right then, the system on chip contains two major parts. We have the PS, the processing system, and then the PL, the programmable logic. The PS essentially consists of two hard silicon ARM Cortex A9 CPUs, which both share a memory controller, which allows both of the CPUs to access a discrete 512 megabyte DDR RAM chip, which sits on the FPGA development board. The board also encompasses a Realtek PHY chip, which is used to deal with all of the, which is essentially a transceiver, used to deal with all the low-level Ethernet protocol things. And we'll talk a little bit about that later. And then lastly, we have the PL, the programmable logic. And this is essentially the standard FPGA fabric that you probably all know and love, which is sort of a mixture of sequential and combinatorial logic blocks that can be programmed using a standard hardware description language like System Verilog or VHDL, for example. Okay, so delving a bit more into what we did inside these blocks. So the PS, the ARM cores, we used essentially as a vehicle to transport operand and operation type data from the host, so from PyTorch, over to the accelerator itself, which we'll discuss later. We decided to use TCP over Ethernet for this sort of PyTorch to hardware accelerator link, as it serves as quite a realistic interface, as it's used in sort of many situations where you have networked FPGAs communicating with one another. So we thought it would be an appropriate mechanism to use in our project here. Because the Realtek PHY chip and the Xilinx MAC IP, which isn't shown in the diagram, it actually only interfaces with the PS in our board, we had no choice but to use the PS as sort of a medium for communication, like a bridge between the host and the accelerator. But the ARM cores themselves were not used for any kind of PyTorch computation. They were simply there just to facilitate the TCP connection and send data to the accelerator. So in our design, we actually only used one of these ARM cores. The other ARM core was kind of left alone. So in one of the ARM cores, we had two threads running. We had one which negotiated the TCP protocol and communicated with the Realtek PHY. And we used an open source library to do this called LWIP. And then we had another thread to decode the received payloads into operands and sort of the operation, the matrix multiplication or the convolution coming from PyTorch. So essentially broke down this payload into these series of tensors, and it would write this to the DDR RAM using the memory controller. And then moving to the PL then, we used this to house a 32-bit Microblaze 5 RISC-V soft core. And this is what we use as our accelerator. The processor has access to the same memory controller that the ARM cores do, which allows it to access the same DDR RAM that the ARM cores do. And this can be done through an AXI interface that we'll talk a bit about later. So essentially, what this allowed us to do was use the DDR RAM as sort of a shared memory region, which allowed the PS, the ARM cores, to send the operations to the Microblaze V core to compute, and then the result was returned back to the PS and then to the TCP link via this sort of a shared memory region. Okay, so now bringing the software side back into the diagram, we have PyTorch. We have the PyTorch dispatcher communicating to the OpenCL runtime via our SYCL operation kernels. Inside the runtime, we have our own interposer C++ program, which is capturing these OpenCL API calls, extracting the operands, i.e. the tensors, and what kind of operation PyTorch is trying to do, packaging these up into a TCP packet, and then sending them off to the Zinc board, and then facilitating the reading back of the results, and then sending this back up to PyTorch. Okay, so I just wanted to include this image here as well, which is from Xilinx Vivado, which is the software package that we use to design our FPGA images. And I just wanted to show this to help kind of illustrate all of the moving parts that we have going on in the FPGA. So first of all, we have the Microblaze 5 processor at the bottom left with the big RISC-V logo. And then you can also see the PS, which is at the bottom right, which is the Zinc 7 processing system. And this also encapsulates the shared DDR memory region that we were talking a bit about before. We have a AXI Smart Interconnect block in the middle, AXI Smart Connect block. And this is essentially an AXI crossbar, which allows all of the input slave AXI ports to talk to any one of the output master ports. And we use this to connect up the two highlighted ports, they're highlighted in red. There's the master AXI DP port, and there's on the Microblaze V core, and then we have the slave AXI high performance port on the Zinc PS block on the right. And this is essentially what allowed the Microblaze 5 core to make AXI memory mapped accesses to the shared DDR region and gain access to the tensors it needed to perform its calculations. Now, because we were using shared memory between two processors as our sort of inter-processor communication, it was really important that we made sure that all memory accesses were completely safe, and we didn't have any situations when a processor, tried to read a memory location at the same time as the other processor was trying to write to it, or have any kind of race conditions. So we used 4 AXI GPIO blocks, which can be seen on the top right. And these acted as sort of like a hardware mutex handshaking mechanism where a bit was set, essentially locking up memory for one of the processors to stop the other processor from accessing memory at the same time. Okay, so to kind of summarize all of this, we have instantiated a RISC-V core as our hardware accelerator on the FPGA, which is running PyTorch operations. The operands for these operations come from the SYCL kernels integrated into PyTorch using the C++ extensions tool that Lawrence mentioned. And these are operated on by the FPGA accelerator, and then the results are returned back via the TCP link back up to PyTorch. So although we actually had to write these SYCL kernels into PyTorch, the fact that they now exist and they are kind of one OpenCL layer removed from the hardware means that operations can run on any hardware endpoint without having to recompile or write hardware-specific code. All the user really needs to do to add support for their own custom hardware is to write some extra lines in the interposer and tell the interposer how to essentially take the data that has been extracted from the OpenCL cores and then turn that into a sort of some kind of communication medium to their hardware, whether that's PCIe, CXL, or some other kind of communication mechanism. But the point is they don't have to recompile or edit PyTorch. They can use the AI tools as they stand, which is really important. Okay, so our demonstrator has support for PyTorch's add, batch normalization, and conv2d operations, as these were some of the sort of major operations used in the image classifying ResNet 18 model, which we tried to use as our sort of benchmark. So in terms of our success then, we were able to build hardware support and SYCL support for the add and for the batch normalization operations. And we were able to build SYCL support for conv2d, but due to sort of insufficient time during the project, we weren't able to actually get conv2d working with hardware. We weren't able to kind of accelerate that operation, but we were for add and for batch norm. And then all other operations were directed to the host CPU via the dispatcher. Okay, so importantly then, the point of this project was to actually make something real. So I can't not show you how that actually all kind of works and is used by a user. So here I've got a screenshot from a sort of a wider Python program that's used to test our add operator. So you can see the first line is using our own sickle add operator, which is essentially going to run a to sort of sensor add with a sort of scalar value alpha. And that will direct that via our sickle to our FPGA, and that's what's happening in this line here. A and B are our input sensors, and alpha is our scalar value. And then we have the bottom line, which is PyTorch's native add operation, which will be directed to the CPU. And we've used the same operands here, so A and B and alpha, so the results should be the same theoretically. So if we run this wider program in our WSL2 environment, we can see our program first just prints out the randomly generated input sensors A and B and a randomly generated value alpha. And then further down the interface, we see the interposer kind of kicks into play. We see it's just detected that it's an add operation, and we can see that it's successfully extracted the operand A and the operand B, which match up with the numbers from the sort of previous image to the left. And then it's identified what that scalar value is. And you can see some debug information here saying that it's connected to the client, which is our FPGA, and then it's sent down the information over to it. And then finally, then we get our results back. And what we've actually done here is print out the native answer, the native result, side by side with the FPGA accelerated answer, just to prove that the two values are exactly identical and that the functionality of the accelerator is kind of correct and mirrors exactly what the standard PyTorch add is trying to do. So our system works with input tensors for up to 512 doubles in size, and this can be for any rank and any dimensionality for the input tensors. And this is true for the add and for the batch normalization operations. And as I was saying, we have sickle support for the conv2d operator, but hardware support was not built due to sort of insufficient time. Okay, so now that we have everything working, there were sort of two main interesting points to note and two sort of things we wanted to investigate further. One of the first things we did was actually change the hardware accelerator to prove the hardware agnostic nature of our system. So you can see here this diagram, we have the Microblaze V core from before, where we actually took this and changed it for the older Microblaze Classic core provided by Xilinx. Now this is another 32-bit RISC soft core, but it's not RISC-V, and it actually uses a completely different instruction set to the Microblaze V core. And upon this change, we were able to run all of our previous examples or our add and our batch normalization operations with random numbers. And we didn't have to, we could do this perfectly with correct results without having to change a single line of PyTorch code, PyTorch backend code, which is kind of one of the most fundamental goals of our project. We're essentially able to mimic the fact that an engineering team have changed their hardware or have upgraded their hardware, for example, and they were able to use the same AI tools, the same code with different hardware using this kind of sickle system that we've built. And then lastly, we were able to have a little bit look about performance. So this is an interesting one. So we were able to use PyTorch's benchmarking feature to time our offloaded operations with the native operations. And sort of unsurprisingly, we found that the accelerated operations were actually far slower than the native ones. But this was sort of to be expected, as the operands for us have to go through many layers of software, like an interposer, the OpenCL layer, an entire TCP session, which is relatively slow, all to reach a 32-bit soft core that only runs at 100 megahertz. So in our case, in our system, it was to be expected that our operations wouldn't actually speed up PyTorch. But we weren't particularly upset with this result, as the aim of the project wasn't really to actually sort of manifest a speed up in PyTorch, but rather to provide sort of a viable and a simple way to bring up and add custom hardware support in PyTorch in sort of an elegant way. And we kind of feel like we've achieved that. So to conclude all of this then, what did we do? So we achieved hardware agnostic PyTorch offload, which is sort of one of the most fundamental goals of the project. And we did so using a sort of relatively cheap FPGA hardware solution. So we used a Digilent FPGA board that only costs around 200, 300 pounds. So we weren't using, expensive hardware. We were able to investigate sort of an OpenCL interposer method of sort of cheaply extracting the data without having to go through sort of more layers of software and having to create OpenCL devices or set up a oneAPI how. And that sort of brings us to the other side then. So what didn't we do? So obviously we weren't able to accelerate PyTorch as we've mentioned. We also didn't, as Lawrence mentioned, sort of get time to look into oneAPI how, which is another tool to streamline the sort of SICL to hardware communication. So it'd be really interesting to see sort of to work on that in the future potentially. So on the topic of sort of future work then, it would be great to see an expansion to our current suite of SICL kernels. So we have conv2d, batch norm, and add written as kind of quite generically as possible, as opposed to the other more sort of Intel-specific PyTorch SICL 2.4 editions. But it'd be interesting to see sort of the creation of more of our sort of hardware-agnostic SICL backends into PyTorch. Another thing as well is it'd be interesting to see an actual sort of try and manifest an actual speed up of PyTorch using a much more expensive demonstrator. So as I said, we use quite a cheap FPGA, which uses quite a slow TCP link. But in reality, if you were actually trying to make a quite performance system, you would use a much more expensive FPGA with PCIe transceivers, CXL transceivers to actually make sort of direct memory accesses to the CPU's local memory, the host CPU's local memory. So you can make sort of much faster memory transactions between your accelerator and your CPU running PyTorch. And then an investigation into oneAPI how I think would be very interesting. Okay, so before I finish, I just want to show just to prove it all works, a little demonstration video that I have here. So hopefully that's playing through. So you can see my laptop there and our Zybo Zinc board there connected up via our Ethernet cable to my laptop. And I'm just running here the same script that I've shared pictures of before. So testing the add operator, and then we can see as I zoom in, this just shows that the two results are in fact the same. Okay, so that concludes our presentation. So we will share these slides, as Jeremy said. We have our GitHub link as well, as all of our work's freely available, including all the FPGA designs. So we'll make sure that that's available. So yeah, it would be great to open up sort of for any questions.